Good morning, everybody. Today we're going to be talking about block diagrams, how you manipulate block diagrams and steady state errors. So we'll talk about how block diagrams are used to represent control systems, and then how we can manipulate them to suit what we want to do with them. We'll go through an example of block diagram manipulation. We'll talk about steady state errors, and then we'll do another example at the end of the lecture. So, block diagrams. Well, we've seen block diagrams before already, but basically it's a system can be represented using block diagrams. And so it's a pictorial representation of a control system. And generally you have these blocks, which are unidirectional. So if something goes into the block, something comes out of the block. And each block represents a transfer function of some description. That could be as simple as just a gain, some value, or it could be a very complex transfer function. And there are three basic elements. We have rectangles, which are these operators. That's where the transfer function sits. We have lines connecting the blocks, and that represents the signal. And then we've got circles, which are summing junctions. So that could either add two signals together or subtract signals from each other. And they're the three basic elements. There are some other elements that you may come across, but this is essentially what we're going to use to represent control systems. Now you know that if you have a very simple, we've got a y as the output, x is our input, you multiply x by a, you get an output of y. Well, that's represented here. X goes into the block, which is in this case is just a as some constant, and you get your output y. So y equals a times x. Very simple to understand. Here we've got a summing, or a subtraction, and you can see that if r goes in and you subtract c from it, you get the output of e. And so we've got r coming in as a subtraction, r is positive, c is minus, okay, c comes in, you get a operation here, which is a summing, and the output is e. So e equals r minus c. Something a bit more complicated. Well, here we've got y equals ax minus bz. Okay, well, ax we saw. You have a block called a, x is the input, and you get an output, so ax. Bz is the same thing. You've got a block with b in it. Z is your input. Okay, b times z. And we want a summing junction because we've got a minus sign in there. So ax minus bz equals y. And that's how you represent that equation with a block diagram. Now with control systems, this is just with variables, random variables. With control systems, okay, the classic control system is a simple closed loop system where you have an input, then you have a process, and then you have an output. And this is a closed-loop control system because what we're doing is we're taking the output, measuring what the output is, and providing some feedback. And then with that summing junction, the input minus the feedback will give us the error. And that error can then be used to drive the system so that we're getting to the point that we want as the output, okay? And often what we do is we represent the process as some transfer function g, we call that g, and we represent the sensor or the transducer as the transfer function h. Okay, input is r, c is the output, e can be used to represent the error, and then b, we use b for the feedback. And so these are the standard sort of letters that we use for the various things. Okay, it's quite useful to know that r is your input, c is your output, e is your error, and then we've got g and h as our forward transfer function and feedback transfer function. We don't use b quite so frequently, but we'll use it in this case just to talk about the feedback. And so let's put that transfer function back up. So we've got these letters r, e, g, c, h, and b. And if I want to work out the transfer function that represents the whole closed loop, okay, I want to, as we know, transfer functions are always output divided by input. Okay, so I want a transfer function. Here I've got a whole bunch of transfer functions, g and h. Okay, but I want one transfer function, one block that will represent R and C. Okay, or C divided by R. And so I can do some mathematics, some simple algebra. We know that the error is going to be our input R divided by the feedback, minus the feedback B. Okay, because we've got a summing junction. We know that E equals R minus B. We also know that B is going to be C times by H. Okay, C times H equals B. And we also know that C equals E times G. Yeah? E times G equals C, C times H equals B, and E equals R minus B. So there's a way to link all these things together. Now if I rearrange that last equation, C equals G times E, I know that E is going to be C over G, because I've just divided both sides by G. I get E on its own. I can then stick E into this equation, okay? E minus, so I've got C over G, I've replaced E in this first equation, and I've replaced B in this equation with HC. So I get C over G equals RS minus HS C of S. Okay, so I've gotten rid of all the B's have disappeared, and I've gotten rid of all the E's. And so I've got something that talks about G and H and C and R. So I'm getting close to what I want, because obviously what I'm looking for is C divided by R. And G and H are just the transfer functions of the system. There's no B or E in this equation. So again, I take this equation, I do a bit of manipulation. I put all the C terms on one side, okay, so I've moved this one over to this side. I've then taken out that, and I end up with 1 over GS plus H of S equals R of S. So I'm getting close. I've got an R of S on its own, and I've got a C of S on its own. And we know that what we're looking for is output divided by input. And so I do some more manipulation, divide both sides by R of S, and then divide both sides by this, and do a bit of mathematical manipulation. I end up with this equation, which is known as the closed-loop transfer function. And what we have is we've got the output divided by the input, C of S over R of S. When you've got a simple closed-loop transfer function where the forward path transfer function is G and the feedback path transfer function is H, then you can say that the transfer function representing this whole system is G over 1 plus GH. Remember that, G over 1 plus GH. Any closed-loop transfer function can be represented by G over 1 plus GH. And so what we can do is we can take that system and we can say that R of S times by this transfer function equals C of S. And so what I've done is I've compressed that whole loop, okay, into one block. That's very useful. And we'll see why that's useful in a moment when we talk about manipulating and in the example when we want. So when you've got complicated things in G and complicated things in H, okay, and you want to work out what C is with respect to what R was, okay, then you can compress it down into one block, which is what's happening here. What about if we've got a feedback of 1? Okay, so we've replaced H of S. We've said that that equals 1. Well, now obviously B of S, is it going to be equal to C of S? Okay, because obviously anything times by 1 is the same thing. Okay, so BS equals CS, and we can do some manipulation. Well, we take the transfer function, and obviously we replace this with 1, and we end up with G over 1 plus G. So if the feedback transfer function is unity feedback, then your transfer function representing that whole closed loop system is G over 1 plus G. This is quite useful to remember for the future. What about what we know as the open loop transfer function? Well, when you've got a system, and we will talk about the open loop transfer function, because there's various things that we deal with when we actually want although the system itself is closed loop, we want to do some analysis based on its open loop response. Well, what you do is you just cut off where the feedback feeds into the summing junction. Okay, you just disconnect them. And so this time, the error is just going to be the input, okay, because nothing else is happening here. And you can do some manipulation again. we know that the feedback, B, is going to be C of S times H of S. And the error is the input, like I said. And so the open loop transfer function, to get the relationship between B and R, obviously you just follow the loop. We've got G times by H. And so B over E is just going to be G times by H, GH. That's known as the open loop transfer function. Again, obviously if this is 1, then the open loop transfer function is just G, because that's the only block that it passes through on the way to B. Okay, so that's the sort of fundamentals of a closed loop systems. But there's various ways that we want to be able to manipulate block diagrams, because they can be a lot more complicated than a simple G and H type system. Okay, and so what I'm going to go through is I'm going to go through a list of different scenarios that you may want to employ and how you can deal with them. And so the first simple example, combining blocks in series. You've got 2 blocks. Let's say that my forward path transfer function had 2 blocks instead of just 1. Well, we know that the relationship between x3 and x1 is going to be those 2 blocks multiplied together. And so to get x3 from x1, you just do g1 times by g2. Okay, and obviously multiplication is commutative, so you could say g2 times g1. It's the same thing. So that's what happens when blocks are in series. Let's say you've got a summing junction and you want to move it. Okay, well, let's move the summing junction to the other side of the block. And so if I've got x1 coming through, I subtract or add x2, that's what that means, okay? Then I've got some signal here, multiplied by g will give me x3, okay? Let's say I want to move the summing junction to this side. Well, what do I have to do to x2? Well, I've got to multiply it by g here, so that whatever comes out here will be equal to what comes out there, okay? Because if you think about it, I haven't got a whiteboard. Let's see. Is the pen around here? Okay. In this case, we've got x3 move the mouse out of the way, equals, think about it, that's g times by x1 minus x2. x1 minus x2. Assuming we're dealing with the minus sign there, okay? Minus. And so that's going to be g x1 minus g x2. Okay, so that's what we're looking for. And here we've got x3 equals, let's take the minus sign. That's going to be g x1 minus g x2, which is exactly the same thing. This is the same as this, okay? And so by putting the g here, you can then move the summing junction to the other side of this block. Okay, but you need to multiply x2 by g, because in that one, x2 is multiplied by g as well. What about moving a pickup point? So let's move to the other side of g, okay, and here we've got x2 being drawn off of the output. Okay, so here x2 equals x2. But now I want to move that pickup point before before g. And so obviously if in this case, x2 was multiplied by g before it was taken away, okay? But here, because I've got a g here, I need to put a g here as well, because I've moved the pickup point from this side of the block to this side of the block. So I need to multiply it by that block on its way through as well. What about the reverse? I've got x1 there. I want to move it to the other side of the block g. Well, if I multiply something by g, to get rid of that multiplication, I need to divide it by. And so what happens here is we have x1 being multiplied by g to give me x2. Well, obviously, to get back to x1, which is what's going on there, I need to divide it by g to get that x1 back, okay? So that's what we do, 1 over g. What about moving summing points? Well, they're a similar operation. Here you've got x1 and x2 coming into that, x1 times g coming into that block, that summing block, giving us x3. If I move the summing point before that thing, okay, obviously I need to divide x2 by g so that when I multiply by g, I just get x2 on its own, which is what's happened there. Okay. So when this comes through, obviously this x2 as part of that function going into g, okay, will be multiplied by g, but obviously here there is no g on the feed in, okay, so I need to divide it by g beforehand so that when I multiply by g, it becomes 1. And we can do the same thing. And we talked about this, eliminating a feedback loop. So you've got g and you've got h. Then that obviously becomes 1 over g over 1 plus gh. Okay, and notice that if you've got a minus sign here, okay, so negative feedback, which is what is the most common, you can get positive feedback with some systems, but negative feedback, then that minus sign, because it's on the bottom, it's the plus sign here. Don't get that confused. G over 1 plus gh for negative feedback loops. So let's go through a little example. Here's a system, okay, and you think, oh my god, there's a lot of blocks there, I need to try and simplify it, because I want one transfer function between C and R, and I've got loads of transfer function blocks in here, got lots of feedback loops, okay. But what you do is you start always from the middle generally. The simple case, let's start here. And so we want to eliminate this feedback loop between C and J, okay, and we've got G3 and H1. Okay, so let's consider the subgroup containing G3 and H1. Well, we know that when you've got a feedback loop, it's G over 1 plus GH. Okay, so here we've got G3 over 1 plus G3 H1. Okay, G3 over 1 plus G3 H1. And what I've done is I've called that G4. And so you can replace that loop with one block, G4. Okay. Now here we've got two blocks in series, G2 and G4. So we can combine them together because we know what to do with series blocks. And so I can replace those two blocks with one block, G5. And again, I've suddenly got another feedback loop between G5 and H2. And so now between C and A, okay, C divided by A is G5 over G5 H2, because that's a feedback loop, G over 1 plus GH. And I can replace that with one block, which I'm going to call G6. And so suddenly I've now got this, again, just a big feedback loop. Okay, and so here H is 1. And so the relationship between C and R is going to be, we know what blocks in series, G1 times G6, over 1 plus G1 times G6, because H is 1. And so this is our transfer function. So we replace that whole thing with a block. And then what I've done here is I've just resubstituted in the various things that we use to calculate G6 and G6, yeah. And so I end up with the transfer function being this down here. And so obviously that looks quite complicated, but what we've done is we've reduced that whole group of feedback loops into one equation. Okay, so I could replace this whole system with a block between R and C that had this inside it, and that would represent what we had to start with. So that's how to manipulate transfer functions. You'll get plenty of practice on your tutorial sheet. There's a few problems for you to go through. They're quite cunning, and you've got to think about them, how to manipulate them properly. But you know, they are all possible, and the solutions will be online next week at some point. Steady state errors. Okay, so we've covered how to manipulate transfer functions, and we also looked at the error signal that is fed back into the main forward loop transfer function when you want to when you have a closed loop system. And we use feedback in systems to reduce the steady state errors. If you've just got an open loop system and there was some disturbance that was affecting that output that you have no control over, okay, then there'll be some error associated with that output, okay. And because it's an open loop system, you've got no idea that there's that error occurring, okay? So imagine driving on the motorway, okay, and you think that I know that pressing the accelerator by an inch will make me go 70 miles an hour, but there's no speedometer, so you've got no idea whether, if you press the accelerator an inch, you think, okay, well, that's going to be 70 miles an hour. But say you approach a hill, obviously the car will slow down, but you've got no idea that you're going slower than 70 miles an hour, because as far as you're aware, pressing the accelerator an inch will be 70 miles an hour. So that's an open loop system. Obviously, the moment you close the loop by having a speedometer, you can then notice that you're slowing down. You can press the accelerator more, and that will be a feedback loop, okay? So feedback obviously helps us to reduce steady state errors, okay? But you can still get errors in systems even if you've got some feedback, okay? And we talk about steady state because that's after this transient has died away. We saw last week that we had you generally got an exponential response even with first order and second order systems, and that exponential relates to the transient response to that system. So that could be the oscillation, that could be just the climbing to your end point. Okay, and once that's died away, then you're in what's known as steady state as time goes to infinity. Now we looked at final value theorem last week, or the week before perhaps even, okay, which is looking at the final value that you get as your output. This time we're going to look at the actual error that's being fed into your forward loop transfer function. And if the error is obviously unacceptable, then the control system will need some modification to make sure that you can get rid of that error. And there are errors evaluated using our standardized inputs. We covered a couple of weeks ago, step inputs, ramp inputs, and sinusoidal inputs. Okay? Step inputs and ramp inputs is what we covered. Sinusoidal inputs, Neil will be talking about next week. So, let's look at an example. This is no steady state error. We've got a second order system, you can tell, because it overshoots and oscillates for a bit. And the response ends up being your input. In this case, input is 1. Nice and simple, no steady state error. What about if you have so there's the transient bit and there's the steady state bit. Okay, so this is what I was talking about. This bit is where it's varying, so that's the transient. And after this point, after the settling time, remember we talked about settling time, within 5% of your final value, okay, well that's going to be the steady state. That's what we consider to be steady state. Before settling time, transient, after settling time, steady state. Well, what about if you've got a system where your input there 1, and you operate the system and it settles, okay, so we're within a settling state, within 5% of our final value, but the final value doesn't match what we want, then you've got, obviously, in there, you've got an error. Okay? And you can calculate the quantity of the error by using the final value theorem, because obviously this is the final value theorem will give you this value, okay, that value is the blue line, okay, and we know what our input was, so you can use the final value theorem to work out how far away from the error signal from the input signal you are, okay, that's the use of the final value theorem. But say we wanted to look at what's being fed into the control system to work out how, what the error, what the output will be, okay, well we can use something similar to the final value theorem to calculate the steady state error signal. Now, steady state error can be caused by a number of factors. Could be something to do with your instrumentation, your transducer. Let's say it's feeding back the wrong signal. There's some damage to it, perhaps. If the system's nonlinear, okay, dead bands or hysteresis. Think about a typical example of hysteresis would be, you're having a shower and you've got your temperature control knob, and you get in, it's a bit cold, so you turn it up, and suddenly it's too hot. And you've hardly turned it up, so you turn it down a bit, it's still too hot, and then you turn it down a bit more, and it gets too cold. You think, hold on, So basically, you've got what's known as a hysteresis loop. When you're moving upwards, you go up one line, and when you're moving back down, you move down the other line. Okay, that's hysteresis. So that's a non-linearity, and that can cause steady state error. Form of input signal, okay, depends on what's being input, and we'll cover that in a second. Although you can get no steady state error with a step input, you can get steady state error with a ramp input for the same system. What the transfer function looks like, okay? And I talked about external disturbances acting on the system. So let's say you've got your car and you blanked, there's no speedometer, obviously that's going to give you a steady state error when you hit a hill or something. And let's say your car is not very powerful, even if you've pressed the accelerator fully to the floor, you still can't reach 70 miles an hour, then obviously that's an example of a force that's acting on the system which will cause a steady state error. Now we looked at our closed loop transfer function, and E we know is our error. And so you can make some calculations. E equals R minus B, which we've seen. Okay, and B we know is H times C. And we know that C is G times E. Okay, so again we can replace, we've got E here, and we want to look at the relationship between E and R. Okay. Well, we know that E is R minus B, which we know B equals this. And here we've got an E, an R, and a G and H. And so you can do some manipulation, take the E, move the E terms to one side, take the E out, and then divide to get the transfer function. And we end up showing that the error signal, or the error transfer function, E divided by R, so this time the output is E, input is R, is 1 over 1 plus GH. Closed loop transfer function was G over 1 plus GH. Error signal will be 1 over 1 plus GH. And that makes sense, doesn't it? If you took C, okay, well that's going to be the error, which is this, multiplied by G. So you end up with G over 1 plus GH. Obviously, to move back to the other side, we need to divide by G, so that G becomes 1. 1 over 1 plus GH is the error. And so say we wanted to calculate what that signal was going into our block, the error signal going into that block. Well, we take our transfer function, we multiply it by our input, whether that's a step or a ramp or whatever, okay, and you get a value for E of S, okay, which will be the signal being fed into the for loop transfer function, or error signal. Okay, and that depends on the system. You know, obviously, if you've got a gain of greater than 1, then it's going to be greater than 1, and that is obviously dependent upon the input, 1 over S or A over S or A over S squared, whatever the input is. And so to work out the steady state error, we can use the final value theorem, but instead of the output being here, we've got the error. Okay, this is the error with respect to time as time goes to infinity, and obviously in the S domain you can say that's S times the error in the S domain as S goes to 0. Okay, obviously S is d over dt. As S goes to 0, that means that any transients with respect to time will go to 0. Okay, because as time goes to infinity, S goes to 0. And so let's say we've got an input, a step input, okay, or we could have a ramp input, and obviously A is the step velocity or the step amplitude. And so let's look at an example. We've got a transfer function, 1 over S times the quantity 1 plus torr S. Okay, so obviously without the S here, we've just got a first order system, but because we've got another S at the bottom, it's a second order system. Our feedback transfer function is 1. And so we know the error transfer function, 1 over 1 plus GH. So we've got 1 over 1 plus, obviously H is 1, so it's 1 over 1 plus G. And what I've done here is I've multiplied the top and the bottom by the denominator down here. And I end up with S times 1 plus torr S. And obviously this times by 1 just moves up, plus 1. Okay. And so I've got my error transfer function with relating the error to the input. I use the final value theorem, so that's just the previous equation. My input is A over S, assuming a step input. And so steady state error is S times e to the S. Don't forget the S here, okay? So I've got an S here, there's my input, and there's my transfer function. Obviously, well, those S's cancel, okay? I can't cancel those S's because there's a 1 over here. But if I set S to 0, obviously that's 0 over 0. 0 times that quantity is 0. 0 times that quantity is 0. I get A. That's 0 obviously times by A as well. So anything multiplied by 0 is 0. Okay, so that's why I get 0. So there's no steady state error with this system. Okay, with the step input. Great, that's what we want. What about with a ramp input though? So there's the output, sorry. So there's my input. You can see it's a second order system because it overshoots and oscillates. There's my input and there's my output. No steady state error, 0. Great, that's what I'm looking for. What about a ramp input? Well, we know that this time the input is A over S squared. That's representing the ramp input. R of S is A over S squared. I apply the steady state error theorem, or final value theorem with the error. S times e to the S. Okay, well, I've got an S here. S squared on the bottom now. Okay, I've got S over S. And so that S will obviously cancel with the 2 there. Okay, and I can cancel out the s that was on the top. 2 s's and 2 s's there, so they cancel. I end up with 1 times 0, 1 plus 0, sorry, times by a, so I get a on the top. In here I get 0 times by that, so that's 0 plus 1. So a over 1, I get an error of a. And so if you look at the output, okay, you've got some transient at the bottom, okay, and then after, if you remember, we said at 4 time constants, okay, then you have a lag. You assume your steady state, okay. A is the error between our output and our input, okay. We want to be here, but we're actually here, and so that's obviously the error of A. Now what about, let's try another couple of transfer functions. We've got an error here. We've got a input of 1 over 1 plus 2s, so a first order system. And we've got a feedback transfer function of 2. And so our error, 1 over 1 plus gh. Okay, so I've plugged in h is 2, so that's 1 times 2 is 2 over 1 plus 2s. Again, I've multiplied the top and the bottom by the denominator, and I get 2s plus 1 over 2s plus 3. So there's my E over R. Let's assume we're dealing with a step input. Okay, so I put in A over S, which is our step, and you do the calculations again. Limit as S goes to 0 of S times E of S. We've got A over S here, the S's cancel, okay? And we have an S here and a S here, well they're 0. So we've got A times 1 over 3. So A over 3 is the answer, is your steady state error. That's the signal being fed into the transfer function. That's not the output value. Okay, the output value is the final value to them. This is the error signal being fed into your system. And so in this case, the error is not 0, and the output will not be equal to the input, okay, because we have some value for the steady state error. And the steady state output, the CSS, can be also found using the final value theorem as follows. And so this is what we did a couple of weeks ago. Okay, the error is R of S minus H times C of S. So you can say C of S is R of S minus E of S over H of S. Okay, and so that's what this is. Okay, and so we're actually, and we end up, yeah, with R of S over 2. Okay, and so you can say, well, C of S equals this lot. Okay, well, the limit as S goes to 0 of S times that lot. Okay, well, let's see what happens. That's 0, that's 0. Okay, that S can cancel with that S. And so we end up with 1 minus 1/3 times by A divided by 2. And so 2/3 times A divided by 2 is A over 3, because those 2's, that one and the 2 that would be there, would cancel. A divided by 3. And so the error was A divided by 3, and we can see that the output is A divided by 3. And so assuming a response, oh, that should be A equals 1, then obviously the output was 1/3 of our demand, okay, the error. And so the error was 66.6% in this case. What about a ramp input of the same system? Or you can do the sums. Obviously our input this time is A over S squared. That S can cancel with the 2. And so we end up with A over 0. Anything over 0 tends to infinity. So in this case, you've got a system that you can't control. Basically the error, as it tends to infinity, this is having no response based on your input, okay? So that's obviously unacceptable in systems. So, I'm going to review what we've covered today, and then if we've got time, I'll run through an example. If I can work out, what time it is, then I can. Okay, we've got a bit of time. Okay, so today's lecture, we've said that block diagrams can be used to represent a control system, as we've shown. And rectangles represent operations or transfer functions, lines are signals, and then you've got summing junctions, which enable addition and subtraction of signals. And there's a whole bunch of different manipulation techniques to reduce block diagrams, and you get, like I said, you get plenty of practice that on your tutorial sheet, which is already online. And steady state errors can help determine what happens to a signal in the steady state. We looked at final value theorem, okay, well this time we looked at the error signal that's being fed into the transfer function. So there'll be times when you want to determine what the error signal is, instead of just what the output could be. So that's today's lecture. What we're going to do is we're going to run through an example now, okay? And this is an example that you haven't got in your notes, okay? Unless you've downloaded the presentation. But we'll just go through it step by step. We've got an electrical motor used in a closed loop system to control the angular position of an inertial load, okay? So we've got an inertia, and there's an electrical motor that's going to turn that inertia, and it's going to operate based on position, okay? Position of the load, which is directly connected to the motor, is measured by a simple rotary potentiometer. So we've got a motor, okay, and we've got a transducer that will measure the position of that end motor. So we've got a motor, a load, and a measurement of that position. The output signal from the transducer is compared with the input demand, okay, so we've got a feedback loop, okay, and the resulting error signal is passed to an amplifier, okay, so we've got an amplifier that's going to multiply the error signal to drive the motor. The input demand is converted from angular displacement to voltage before being connected to the summing junction. So a lot of words, let's represent it with a picture. Okay, so here we've got a motor, a turntable, a tachometer. This is what's measuring the position of the motor. The turntable is obviously our output. Measurement of the tachometer is fed back to our input. That's the voltage coming in, going through an amplifier to drive the motor. Okay, so we've got there's our system in a picture. And we can represent that with a block. Okay, so input goes through some gain, okay, relating the voltage here to whatever we've got coming in here. The summing junction will give us the error. That goes through an amplifier. That goes to the DC motor, which will drive the turntable to a position, and you get an angle. The angle is measured using the potentiometer, which is fed back and subtracted from our input to give us the error, okay, and so on. And so this will drive the turntable to a particular angle, and that angle is measured and fed back, and we'll keep doing it until you get to the angle that you wanted, ideally. Now we can represent a whole bunch of those things. So there's our block diagram. Electrical motor is used in a closed loop system to control the angular position of an inertial load. Okay, so that's the motor and the load. Position of the load is directly connected to the motor is measured by a simple potentiometer. That's there. And then we've got the output signal from the transducer is compared with the input value, and the resulting error signal is passed to the voltage amplifier. So that's there. And the input demand is converted from angular displacement to voltage before being connected to the summing junction. So that's where that gain comes in. And so we can replace all these things with equations, okay, because they're all transfer functions. So the torque of the motor is some value, K, times by the current going in. Okay, that's just electrical response. The amplifier, the current is just some value times by the voltage. Okay, the load, this is Newton's second law. Moment of inertia times by F squared times by the angle. Okay, so that's the acceleration of the angle, S squared times that. Yeah, and here we've got the speed of the angle, C times S, so that's the damping. Input demand is some value times by so that would be, say you've got a knob, okay, the knob will be marked up in angle, okay, and then you have some constant, which times by that angle will give us the voltage input. And then the feedback, so this is the voltage output, voltage input, is some constant related to the transducer, and then we've got our output angle, okay. There's a lot of equations. Like I said, you can go through this example if you download the presentation, which is online. Which will be online, it's not online just yet. Okay? And so you've got an error signal, which is obviously the input voltage minus the output voltage. And so we can stick those values into our block diagram. There's our motor, so, okay, which is the inertial load. So that's the turntable, the inertial load. So you've got a torque going in, you've got an angle coming out, that's what we saw. And to work out what the torque going in, well, you need the motor there. To get the current, we know that's some value times by the voltage going in, A, okay? So there's the error voltage going in. Here we've got theta coming out, an error voltage going in. We need to convert the theta to a voltage to work out what the error is. And so that goes to a transducer, which will convert that angle to a voltage, output voltage. And then we've got an input voltage coming in, summing junction. And then to work out what the input voltage is, we've got that. There's our input angle, output angle. And so you can do all the manipulation. Okay, this is another closed loop system. Okay, and so you've got G, which is A times K of M times over JS squared plus CS. Our H of S is KT. And then once you've worked that out, and so H of S, and when you move the summing junction forward in the sense, or backwards, you have to divide by what you're moving it over. And so you can do the closed loop transfer function, you end up getting this as your output. So there we go, there's an example. Like I said, I'll stick these online when I get back to my office, and you can download them and go through that example again yourself. And like I said, the tutorial sheet is online. Answers to last week's tutorial sheets are also online. So you can download. Thank you very much.